So this is joint work with two finance colleagues, Paul Goldsmith-Pinkham and Toby Moskowitz. So three kind of different motivations here. One is, I find it really hard to understand, like, luck. I think skill is, in most cases, I can dissect that in some application. Luck, I think the best kind of general understanding I have of it is that it's kind of residual of skill. It's not very satisfying. A second motivation is in tennis and elsewhere is this long-term interest in comparing women and men. It dates back to 1888, where there was this show matches between women and men with some handicap. In 1973, it was a match called Battle of the Sexes between Billie Jean King, the #1 female player at the time, and Bobby Riggs, like then retired 55-year-old who challenged Billie Jean King, but he was #1 at some point in time. This was the TV viewership was 50 million in the US, 90 million worldwide. Still the most viewed tennis match in history, and it's kind of been like a landmark thing for the kind of acceptance and appreciation of women's top tennis. Today, in the modern era, the most prestigious tennis achievements is Grand Slam, 4 per year, same for women and men, so equal opportunity. And a third motivation was for me to learn. I come from an operation research background, so not doing data, and I'm kind of, in a modeling paper, if I make a mistake, people may think I'm stupid. I would prefer not, but I'm kind of comfortable with that. Working with data, if you make an error there, I think people may think you're a crook. I would not be comfortable with that. So I'm kind of been a bit shying away from it. And then I started looking a couple of years ago at Bayesian inference, and it kind of felt a bit like coming home. It's like notion of generative model and working with synthetic data and stuff. It's like, okay, I can do this without being nervous about, like, am I really doing the right thing and not being influenced by data here? So that's also like a third motivation. And also for that, I really like and appreciate open source software. It's nice to say some appreciation to, like, in person to Stan developers, and especially like learning this stuff. The Stan documentation is like, wow, thank you. That's really good. Okay, so what is a good model? I think some criteria. I think one criteria for me is that it should be simple. I struggle with complicated models. I don't understand them. It's like too many things going on, like a lot of confounding things. Hard to estimate. Like, I like simpler models. Also, it's nice if you can have structure, especially if the problem that you study have a lot of structure to it. Then you can kind of reflect that structure in your model. So kind of like reflecting that structure is, like, if you don't, it's kind of like throwing away data. And tennis, as I hope you agree with, has a lot of structure. Another thing, since we talk about gender differences too, when you talk about structure, it's also maybe come to mind structural discrimination. Let's keep that in mind a bit and maybe return to it. Skill and luck. Tennis skill, like, you can make a long list. Luck, not so clear. Let's think about it at the smallest level, winning 1 point. I'd say a tennis player that has a higher probability of winning that point is more skilled. The luck is got the difference between, do you win it, 1 minus p, or negative luck, like minus p, if you lose that point. And then I can think about skill as, in terms of probability of winning that point, as my main thing, and I can plot the probability of winning a point as a result of it. It's a 45-degree line. But then the point-winning probability feeds into the probability of winning a game. And a game I can draw as a graph, and I can solve it recursively to, which is the formula on top there. I can also do it, it's kind of more messy, and it's nice to have some computer algebra systems. I can do that for tiebreakers also. It's both serving and receiving. For a tiebreaker to first do 7 points is the second formula here. But I can solve that. And I can plot the probability of winning a game as a function of the probability of winning a point in this graph. Then the probability of winning a game is kind of like how you travel on the graph of a set score. So with that, I can calculate this and then plot the probability of winning a set as a function of the game, the point-winning probability, if I disregard serving and receiving for a little bit. And the probability of winning a set feeds into the probability of winning the match, which is also a similar, simpler graph. And here I see that, well, it depends if you play best out of 3 sets or best out of 5 sets. You hear that the best out of 5 set goes up steeper. So what that implies is that if I play best out of 5 sets, you can get more paid for your skill. Right? So the probability of winning the match goes up faster, best out of 5 sets. And we think like, well, maybe it's not that equal between women and men in Grand Slam then, since men play best out of 5 sets and women play best out of 3 sets. But and it is, I know here in Europe, we're very interested in soccer more than tennis, typically. Like, how would soccer be plotted here in terms of if you take the probability of scoring any given goal, it's somewhere between like just winning a point and winning a game in tennis. So soccer is one of the most luck-prone sports in the world, and I think that's why part of the reason why it's so popular in America. And people think they should score more goals. I think it's popular partially because of few goals. So the underdog always have a chance. I think tennis has a luck problem. It's just too little of it. It's too predictable who's going to win. But then this match-winning probability, again, feeds into the probability of winning a tournament. First, I thought we'd need to do this by simulation, but it turns out you can calculate this with this recursive Hadamard multiplication of matrices. So you can do that exactly. And then that winning a tournament probability, again, feed into your career achievements in the number of titles you'd have, if that's what you count. So that would be captured by a Poisson binomial distribution, which you can write recursively as a 2-line function. So in like some kind of overall motivation, I think many of you maybe saw this Federer's speech at Dartmouth, where he said like you even won about 80% of the matches, but only about 54% of the points. Also, in some matches, he won probably more than 54% of points, and some less. So if you look at, for example, his achievements at the different rounds in Grand Slam tournaments, the point-winning probability came quite low. But still, he won a lot more. And also here is plotted Djokovic and Nadal, like the 3 dominant players in modern era for men. If you plot Serena Williams here, she has a quite similar pattern in terms of the number of matches won, but in terms of number of points or proportion of points won, she dominates all of those 3. So it also seems like maybe she did something better here. So to try to look at this, you can build hierarchical model based on a more Bradley-Terry type of model on a point level, like similar to what Bob Carpenter did for baseball. And then adjust for serve and receive, the average of that. Also, some players may have a bigger or smaller kind of difference, tendency between serving and receiving. And then we have the estimation of that. And then by doing, like working with synthetic data, you can try to debug the inference. Data on tennis is really good. So Jeff Sackman has like collected and cleaned up like historical data, like super good. And the way we do this in the simplest way is to take 1 year of data before a tournament, then do the inference for that upcoming tournament, and we do this on a rolling basis. So you do, like for now, a separate inference for each tournament that we're going to analyze. And then looking at one of the nice things we get from this matrix multiplication is that you can also query it to see the distribution, like not only your probability of winning the tournament, you'll also see out of the more than 2 million possible paths you have through the tournament, where like do the best of the other players survive until you face them, or are they eliminated? So that's also part of luck, like how lucky are you going to be with the other results that will eventually feed into your path. I'm not going to show it here, but also you can look at the luck of the draw and how that influences different stages of players. And we can do some counterfactual analysis. Maybe it's not that equal. So Serena Williams, being considered the best modern era tennis player with 23 Grand Slams. Until recently, Djokovic got 24. But is that counting in the right way? So here you can do counterfactual analysis of the men if they had played best of 3 sets, or Serena Williams best out of 5 sets, and see, like, if you look at the matches since 2004, instead of those 17 Grand Slams with best out of 5 sets, you can estimate that she would, in expectation, had 20 Grand Slams, so 3 more. So if you extrapolate on that, maybe she should be considered, like in a fair comparison, 27 Grand Slams. So maybe Djokovic shouldn't retire. Quite, yeah. But if you're number 4 woman in the world, or number 4 in the world, you prefer best out of 3. You prefer more luck. If you're number 1, you prefer only skill, or skill to count as much as possible. Then I also had more educational plans for the summer to look at other factors. One thing I did was to also look at what type of data is available. So not only do women have fewer sets, they also have less point-level data. So going before 2004, it's mostly game-level data. The nice thing with Stan is that you can code up the likelihood using those relationships, and then use game-level data and point-level data together in the same inference. Another thing that is kind of gives me a bit of a headache, like how to, in a right way, do a surface, take into account surface. Since, especially when you do sum to 0 of skill, like, you know that some surfaces are more similar to others. How do you reflect that correlation? So you can do that like in a real value, but if you look at sum to 0, like, and how to kind of project that in a best way, I'm still working on some synthetic data on that. Other things you get into is like this link function. Is that really? It starts to matter what kind of link function you choose here. So think about this. What's happening here is kind of like a nested Jensen's inequality. And also where the link function is curving matters. And the uncertainty of skill kind of gives a positive correlation between the serve and receive effect, while the serve and receive effect has a negative correlation of those two. And another thing is that the uncertainty, like the unexplained uncertainty between matches, also kind of matters here, because by this density inequality, like carrying up. So it's like in the summer I've been working a lot on, I think as much with probably more with pencil and paper to understand what's really going on modeling wise, and then trying to look into simulating data, and again like try to have confidence in the inference before we let it taste data for those extensions. Okay. So that's quickly my self-study. Yeah.
Great, fantastic, thank you so much. Do we have any questions? Yes, over there.
All right, very cool. I was wondering, you did mention like a couple other features that might be interesting, like the surfaces and everything like this. Are there plans to extend it to other interesting information? Because there's a lot of matchup, features. Like some players are really good playing against certain players, but really bad playing against other players because they're short, tall, or fast, not fast. You know what I'm like? Those kinds of features, and then there are a lot of things that you might also have data on, like the weather, the conditions of heat, and so on. Some like Sinner, for example, is really bad playing in heat. Those kind of things might also matter. So, are there plans to condition on that kind of stuff?
We've been thinking about it, and we have a long list of those things. But it's also a bit like a reverse peeling over the onion to try to get the core working before considering those things. So I think so first like having like the surface and really like the inference working, and like what's the best thing. And also, it can be a lot of unobserved things if a player is injured or didn't sleep well. So also measuring some of those latent things before, and you also have like psychological effects and those things. Yeah. But before starting looking at that, at least we need a good base level. Will we ever get to like if player A against player B, like is something happening like in the air? I don't know. But I think it's one thing for sure is a lot of opportunities, and it's very good data, and it's kind of a really nice example of like because of the structure, maybe you can get something sensible out of that.
And maybe even like temporal, correlation as well, because some players they play very well for a long stretch of time, and then that might be a good predictor for how they perform in the next match and so on.
Yeah, but then like what's causing it, I don't know. But you can think about some kind of like variation of Onschen-Uhlenbeck process where you have your peak performance at the level, but then injuries or like you have problems with your partner, like whatever, like drives you down, and then you have some drift back up again. And then you have some career projection, but we have a list of those things, but it's like that's definitely not this summer. So.
Yeah, thanks.
All right.
Yes, was there one more?
I think we have time. Just at the back there.
Yes, hi. Thanks. I always enjoy a sports presentation. Two short questions. First, you mentioned that soccer is much more random at the game level than tennis. I guess you tested that. Did you try also on baseball? Because baseball is more like it's a very interesting game because it's very random at the game level, but then they play so many games during the season that the distribution just converges to what the true strength of the team is. Yeah. So curious about that. And second question is, What's your end game with this kind of model? Like, do you see these kind of things applicable in the sports industry in some way?
Yes, I think Toby and I teach a course in sports analytics, so a lot of this comes from that. Another interest here is also from labor economics. You know, like if you're lucky with your PhD advisor, maybe get some really good papers, and that's good. Yeah, and also like does luck tend to last? So I think the definition of luck is that like if you're lucky with one coin flip, it doesn't have any prediction in terms of are you going to be lucky on the next coin flip or not. But there are ways, there are like mechanisms that carries luck on. For example, in the labor market, if you get those good papers from your PhD, maybe people think that you're really super good. And more people are interested in working with you, so you have more of a selection, and that carries on. In tennis, with the ranking system, if you're lucky in a Grand Slam with the draw and also who you meet on that path, you're going to get higher rating, a much higher rating, and you may be seeded. And so those points last you a year and may even help you to keep that seed. So it's also to understand like the different notions of luck, not only in sports, but if it can be like some lessons transferable to other parts. So, but like baseball is also a lot of luck, and one of the things is that the number of points you score, I don't remember what you call it, like, it's also compounded. It's dependent in each inning, right? So yeah. But I think one nice thing with sport is that it's a lot of structure that it makes it very nice to build like inspiration, like generative models. And also often there's a lot of data to use that, very good quality data. Yeah. Yeah. Thank you.
All right, another round of applause, please, for Nils.